This covers a summary of particle kinematics, and what I'm going to try and do is talk about the main points of this chapter. This is a pretty dense chapter in terms of material covered. We talked about coordinates, we talked about absolute dependent motion, we talked about relative motion. Relative motion in particular is a bit useful now, but not as useful as it will be in the second half of the course. I just would remind you to think very hard about it and just keep it in mind, not so much for this part of the course, but for the second half. And one thing to remember is that this chapter dealt with acceleration. And this course is worried about primarily Newton's second law, sum of forces equals mass times acceleration. So we're looking at ways of describing acceleration and motion. In terms of coordinate systems, we've tended not to do too much in terms of 3 dimensions, and we probably won't for the rest of the course. But we have a coordinate system that is based on I, j, and k, which is unit vectors I, j primarily. And we have position, which is r, rx, ry, and more typically x and y in the I and j directions. Velocities vx, vy in I and j directions, and acceleration ax, ay in the I and j directions. In terms of the second coordinate system, the main thing is here we have position, which is defined as the magnitude along the path, and that's it. It's not a vector. It's not really used at all in terms of problems when you see this in the course. You just get velocity or acceleration. So what makes that easier is that now when I want to do a velocity is just the velocity acting in the tangential direction. Acceleration is acceleration in tangential and acting in the tangential direction. And because I'm going to have to calculate a unit vector derivative on ut, I end up with a normal acceleration un. Both of these then end up with this expression here, which is at is equal to dv dt and acceleration normal v squared over rho. Final one is the r theta coordinates, cylindrical polar coordinates, and position is important, r, u, r, and velocity is important, but now I'm going to have to calculate a bunch of terms, and I end up with r dot and r theta dot. I have acceleration r and acceleration theta, and these you don't necessarily have to memorize, but you have to be aware that they exist. The important thing too is that Vr is equal r dot, but V theta does not equal theta dot, it equals r theta dot. And that's because you have to have unit consistency. So theta dot has units of rads per second and r has units of meters. R dot has units of meters per second. If you go through all of the other terms, you'll calculate the same thing. We have a separate video looking at unit vectors that you may find useful if you want to sort of go through the derivations. Coordinates do not modify position, velocity, or acceleration. The idea is that you just have a better way of describing things dependent on the coordinate system that you use. So scalar components, however, are different in the 3 coordinate directions. So here I have x and I have y, and that defines that r that goes from the origin to this point where the particle is. I've chosen a projectile motion, and so this is the particle is right now at the top of its path. The NT coordinate, yeah, I could sort of define it this way where it's S traveling along here, and S sort of defines this location right here. And it starts here. But it's only magnitude, it's not a direction, and it's path dependent. Finally, I can use r theta, and that's at an angle, and it goes out to this point here. Same thing, and I get the same direction. But you'll notice that all 3 of those components did not have the same magnitude or anything, actually. Look at velocity. I've chosen this because this projectile is now at the top of its motion, so there's no Vy. It's not moving up or down. Vx is the only velocity there, and with projectile motion, we always assume constant constant velocity, no acceleration. Tangential velocity at the top of motion is going to be Vx because that's the only motion going on, and that's the tangential, so that's coordinate agreement. Then here I have UR U theta, which describe the two velocities, so I'm going to have VR V theta. You can see right away why I wouldn't want to use an R theta coordinate system for projectile motion. And most of the time when we did Cartesian or projectile motion, we used Cartesian coordinates. Same thing with acceleration. Here, the acceleration is only acting in the downward direction. There's a 0x acceleration. And so AY, AN, both are parallel and same magnitude. And there is no AT at this position.
If the particle was at another position along the path, then I would have an acceleration tangential in addition to the acceleration normal, and the problem would be a little bit more complex in NT coordinates.
On the other hand, there is an acceleration theta and an acceleration r. And I'd have to consider both of those as I was going through this problem. Projectile motion depends on two sets of equations: velocity, which is rate of change of position with respect to time, acceleration, which is dv dt, and
if you look at the second expression, ADS equals VdV, you can take the expression for acceleration, which is equal to dv dt, and also recognize that we've defined velocity as rate of change of position over time, ds dt, and essentially, because we're engineers, move dt to the left-hand side and v to the right-hand side, and you end up with dt equals ds over v. That allows you to rewrite the expression acceleration is equal to v dv ds. And that's the second expression we have there.
These two expressions are not independent, and we'll end up not being able to solve for three independent variables, but two. So you have to be aware of that as you solve these problems. Velocity is equal to the initial velocity plus acceleration constant times time. Position is s naught plus v naught t plus 1/2 act squared. And in this case, if I have everything in terms of position, s minus s naught, I can describe it in terms of or calculate the final velocity. Often, and again, there's an advantage for these types of problems. We use Cartesian coordinate system. Projectile motion, we often assume a constant acceleration, or we have a constant acceleration of g, and we end up with three equations for the y component, which is velocity, velocity, and y. Acceleration is just going to be ay equals minus g. If I solve through, and I can solve and put the correct values for each of these terms. Velocity in the horizontal direction is constant, and position is going to depend on only the velocity, not a acceleration x. The thing that we spent a bit of time on was absolute dependent motion.
The orange cord is wrapped around pulley A, pulley C, the corner pulley, and attached to B at one end and D at the ceiling at the other. C is fixed in position.
And if I look at that, I can say, well, I have a constant length to this position about the center of C. SA. I'm not including these things here, but they're constant, so I'll probably ignore them later. I have SA, H, and SB. Length C plus SA plus H plus SB plus these sorts of three values of constants. It's the length total. I can combine them, and I end up with this relationship here. Now, if I take the derivative of that, I have the derivative of a constant length and a constant length, and I only end up, when those terms go away, I only end up with these two expressions, SA dot and SB dot. So SA dot is equal to minus 1/2 SB dot. SA double dot equals minus 1/2 SB double dot. So if B moves to the right, then what will happen is A moves up. And if I have a typical coordinate system, x, y, then what happened is that mass A has moved upward a positive direction, and that doesn't seem to make sense. So it's important to realize these are telling you about the rate of change of the length of A and the rate of change of the length of B. So if you look at SA dot, when it increases in length, B decreases in length. So remember, that's really what you're doing. You're not calculating velocity directly. So you have to look at what the drawing tells you. And when you look at the drawing, it helps you understand a lot more. So this is one of those problems where you can solve the equation, but it won't tell you what you think it is. So remember, this is important. There's different rates of change of the length of SA and SB. SB increases, SA decreases. But the axes may be different, and you need to be careful in terms of defining them. In terms of relative motion, this again is something that is kind of useful and more useful later on in chapter 16 in particular. But when you do this part of the course, we're often looking at, say, two particles, particle A and particle B. And if I want to describe the velocity of B in terms of velocity of A, I can define an origin point over here, and that origin point gives me an absolute velocity. So the absolute velocity of A is VA. But I can also get a velocity of B with respect to A. And so I can do the same with acceleration of A plus acceleration B with respect to A. And I can draw this triangle. So the sum of this plus this equals this. And one of the things to note is, in terms of the notation, is that that allows you, the way it's written, if what's in the denominator is what you want to cross out. It's really important in the rigid body part of the course. It's useful in this part of the course. And you do a couple examples where you look at, say, particles traveling along at different locations. So typical problem is, say, two airplanes going off at 45 degrees with respect to one another. Draw lots of pictures. This course, in particular, when you look at the absolute dependent motion, it becomes clear what the motion is if you take the time to draw the picture. If you try and visualize it without drawing the picture, often you'll end up in a lot of trouble. And this is something I'm saying from personal experience. I find it's very difficult for me to see things and understand what the equations are telling me without looking at the pictures at the same time. So drawing a simple cartoon can be a significant help to you as you go through. Know what the relationships are. And in particular, what I'm talking about are things like AR and A theta, and VR and V theta, and AN and AT. So know how to apply the relationship. So when you look at it, say AR A theta, VR V theta, and AN and AT. This course really is discussed and starts in the next chapter when we start looking at Newton's second law. This chapter has helped us understand acceleration. It's a foundation of the course, but the most important thing is going to happen in the next chapter.